test if we can work.
Yes. No.
Yeah, click on the presentation. No.
And click into the presentation. Maybe? Oh.
Yeah.
Yeah. Oh, just click this.
Yeah. It's not fun.
One stick it so it doesn't fall.
Recording.
Yes.
Hello, everyone. Thank you for being here. Today we have Monish's presentation, who has been with us from fall 2020. Yes, and I remember when he was in our Source CS program, which is incoming students from high school to Lowell. We interacted and then we immediately hired him on one of the projects, which was finished. Can I say finished? Yes.
Applications to go.
Yes, recently. Yes. And then, if people didn't know, yesterday or Saturday, the paper he submitted got accepted, which is on this work. So there is a publication on top of everything. Yeah, it was great working with Monish. He was very active in everything, and we gave him a lot of jobs, and we took care of almost everything. All right, so the structure usually is as follows. So we go through the presentation. Usually we give a few minutes after the presentation for all the questions from the public, and then everyone is out except for the committee members. Then committee members ask their questions, and then Monish is out as well. There is a closed door discussion between the committee members, and then we call him back to give him the results. So if there is anything, there's not anything we can start.
Okay. Hello, everyone. Thank you for coming to my thesis defense. Hope you're having a lovely day. My thesis is titled Enhancing Team Performance in Multi-Agent Multi-Armed Bandits Through Optimization. Thank you. I did this thesis under the supervision of Professor Reza Masade, and my committee members were Professor Hadi Amiri and Professor Amanda Reddy, who gave me great feedback on the thesis and also direction on my work. So a little bit about myself before we get started. I received my bachelor's in computer science from UMass Lowell in spring 2023. I worked in Pearl Lab, like Professor Reza Masade said, since September 2020. And some of my research interests include multi-armed bandits, multi-agent systems, which fall under my thesis work, and also some other fields such as human-robot trust and assistive robots, which I encountered throughout my research experience. So let me talk a little bit about the motivation and the background. Why are we dealing with multi-agent systems and optimization? So multi-agent systems are growing in popularity in fields such as warehouse robotics, search and rescue robotics, and also outside robotics, such as multi-agent systems in IoT devices and traffic systems, where you want to have multiple computers or agents communicating with each other to solve either one or multiple goals. And because we have more multi-agent systems that are present in today's world, there's an increasing need for optimizing these the teamwork or the communication between these systems, so that they can achieve their goal faster and they can maximize their overall reward. And as we said, teamwork is essential. That's a common parallel that researchers use in order to improve team performance. And one thing that we account in this work specifically is we must account when we are dealing with teamwork in a multi-agent system, we have agents that have different capabilities or competencies. So we have to take into account of these differing capabilities in order to optimize team performance. So specifics about what we are dealing with in this thesis, we specifically use the multi-armed bandit problem in the field of reinforcement learning as our baseline for teamwork, representing teamwork. So the multi-armed bandit problem in the reinforcement learning world, it's a decision-making problem, the one that deals with exploration and exploitation dilemma. So an agent is tasked with picking between multiple actions, and behind these actions, that there's a hidden reward distribution that is not available to the agent. And the task of the agent is to sample these actions and then figure out which one returns the maximum reward, and then to maximize this cumulative reward in the long run. And multi-agent multi-armed bandits are the multi-agent version of this problem, where you have a team of agents working together to find out what this best action is. And so what do we mean by the team in this case? Come on. There's a seat here. So what do we mean by the team in this multi-agent multi-armed bandit context? So the team formation, how we represent it in this case scenario is using a relational network. So it is a graph structure that represents which agents are communicating with each other. And the edges in the graph structure have edge weights associated with them that represent how much information is flowing from one agent to the other, or how much importance is one agent giving to the information coming from other agents. And our goal is to find the optimized or optimal edge weights so that we can improve the team performance in long run. And why does this matter? Because the edge weights, the weights given to the edge weights directly impact how the information coming from agent 1 to agent 2 is being used. It is very important to optimize them so that they can reach a consensus faster on what the best action available is, and they can keep taking that action and maximize their overall long-term reward. So in this thesis, our contributions are as follows. We improve team performance by optimizing these edge weights. And in the process, we also look at formulating agent competencies. So as mentioned before, we are interested in considering teams where agents have different capabilities or competencies. We also formulate a bandit difficulty rating measure. So this will be used in classifying bandits into different stages or different kinds of problems. And we also develop a long-term optimization process where the teams play multiple bandits or multiple stages of bandits, and we still want to optimize them over these stages. So we know how the base or the experimental setup is like. So we have this multi-agent multi-armed bandit problem. We want to know how the agents can estimate the means of the arms or the means of the actions that are presented to them. So here we take a look at the algorithm called co-op UCB2. This is based on a single agent UCB2 algorithm in the field of multi-armed bandits. Essentially what the algorithm allows an agent to do is to sample arms and then try to figure out which arm has the best payoff over a long period of time. So this is the multi-agent version of that formula. And here we can see there's a Q value. And if you're familiar with reinforcement learning, Q value is usually the value given to taking an action given a certain state. In multi-armed bandits, there's no state, so it is just the value of taking an action. And we have two different parts to this equation. There's the first part, which is S divided by N. So this is cumulative reward or cumulative estimated reward that the team has received by pulling a certain arm. And the N means how many times they have selected a given arm until the current point. So basically by dividing these two, we get the average reward over up until now. And we also have the second portion, which is essentially a confidence bound or the confidence interval that is given for each arm. So what does this confidence interval mean? So when it should be noted that each of these arms have a hidden normal distribution or a Gaussian distribution. So as you have more samples, we have a better idea of what the mean or the average of this distribution is. So when we have fewer samples, this confidence interval is very big. So that means we are not certain what this average is. But as we gain more and more samples, as we pull an arm more and more, this confidence interval shrinks. And so we have a better idea of what this arm mean is. So the Q value is basically a sum of these two, and then they basically do an argmax, or whatever has the maximum value, and they select that in the next run. So now that we know how the agents estimate the rewards of any arm, we need to know how they communicate this information to their neighboring agents or with each other. So What we rely on is this basic idea of discrete learning or distributed average learning, which is basically you take the node states in the current time step, and then they're broadcasted from each node to the neighboring nodes, and then they're averaged by the neighboring nodes. So we can see, missed something new, but okay. In this case, we have this portion, which is the node states in the previous time step. And then we have the new information that is coming from sampling an arm. So in each time step, they go out, they sample an arm, they come back with that information, and then now they have to broadcast that information to the team. So they add that new information to the previous state information, and that is multiplied by this P matrix. And this P matrix is essentially the edge weights that is represented in a mathematical form. And multiplying that gives, with the new information, gives us the new state information, which represents what this estimated new, what the new estimates for each of the arms are. And so, as we mentioned before, the goal is to find the optimized or optimal edge weights. And there are some methods that give us ways to find these edge weights. And the first category we're going to take a look at is the heuristic methods. So under heuristic methods, there's two different categories. So the first one that we'll take a look at under the heuristic methods is constant edge weights. So essentially, as the name suggests, we consider that each of the edge weights that are not self-loops are constant. And this is the Laplacian-based method. So essentially, all we need to say is that we want this edge weight to be some alpha, and then we can just plug it into this formula, which is based on the structure of this network. And that gives us the output P matrix. And there's a few methods in which we can pick this constant alpha. So the first one is best constant. This exploits some of the network properties using eigenvalues, which it's a whole proof unto itself. But basically, it says that it relies on the first largest and the smallest eigenvalues of the Laplacian matrix in order to figure out what the alpha is. And then there's maximum degree, which is essentially 1 divided by the maximum degree of any node. So in this case, that would be 3. And then there's stepwise maximum degree, which is actually used in the co-op UCB2 algorithm that we are using to simulate the multi-agent multi-armed bandit procedure. And this one essentially adds a kappa value, which is the stepwise variable, which can be manually tuned depending on the network that is being applied to. And so now we talked about constant edge weights. We will talk about local degree weights now. So this essentially says that for any given edge in the graph network, we take the higher degree. So when an edge connects to different nodes, we look at the higher degree of any node that it is connecting, and we use that as the constant, or not the constant weight, but to set the weight of an edge in the P matrix. So we looked at heuristic methods, but there's also some optimization methods that try to formulate this in a little bit more smarter way in order to find the P matrices. So the first one that we will take a look at is FMMC, also known as fastest mixing Markov chain. So essentially how this algorithm works is by reformulating or rethinking this problem in terms of a Markov chain over this network. And when you define a Markov chain over the graph, it essentially means that each of these edge weights is the transition probability of each node from going from node I to node J. So what is the probability of the value at any given node from going from its own state to the next, or its neighboring node state? And so the goal is to minimize or optimize the P matrix. And that is finding the optimal probability of transition. And they do this by finding the minimum mixing rate of the P matrix. And the minimum mixing rate is essentially, it exploits some of the properties of this P matrices. So here it is the second largest eigenvalue. It has some special properties in consensus processes that leads to faster convergence over time. So first, FMMC writes this in a convex optimization form. And so you can see that this is the spectral gap of the P matrix. And this is the same as the second largest eigenvalue. So they're all related to minimizing the mixing rate of the P matrix. And for easier computation, they rewrite this in a semi-definite programming formulation, which makes it efficient and also lets us find the optimized P matrix. And you can see that there's certain constraints here. So the main thing is all of the edge weights have to be non-negative, so they have to be 0 or greater. The rows must add up to 1. So because these are transition probabilities, we want them to add to 1. The P matrix should also be symmetric. So this is to reduce the number of variables, but also satisfy the columns must add up to 1. And you don't accidentally create any edge weights where there are no edges in the original network structure. The second optimization method that we are going to look at is called FDLA. It stands for fastest distributed linear averaging. And this is also very similar to FMMC. So the goal is to approach the average matrix. So as you multiply the initial node states with P, as T reaches infinity, we want it to achieve the average value of the initial node states. So they say, so we can prove that we want to minimize the spectral radius or the spectral gap that is given, that is the same as rho of the P matrix. And this formulation is very, very similar to FMMC in that it also tries to minimize this rho. And it is subject to the same constraints, except one constraint, which is that FDLA does not restrict its edge weights to okay. Someone joined me. So essentially what it says is that FDLA does not require its edge weights to be non-negative. And this, we don't know what it specifically means in a more intuitive sense, like what does a negative edge weight mean when I'm talking to someone in my team. But in some cases, it can result in some faster conversions in specific scenarios. So now that we have the heuristic methods and we have optimization methods, we want to conduct experiments to find out if the optimization methods actually result in better team performance. So we take a look at 6 different small-scale networks. 5 of these are 5-agent networks and 1 8-agent network. And we test these with 10 armed bandits. So there's 10 actions to take to sample, and there's only 1 best action in these available actions. And we average performance across 10,000 times runs so that we get an average team performance. So we'll take a look at one specific scenario first in order to understand what this graph means. So essentially what we're looking at here is how the error or the difference between the estimated mean for the best arm is from the true mean of the best arm. So initially, when the agents don't have any idea of what the true means or the average payoffs of the arms are, the error is very high. And then as they get more idea, as they gain a better understanding of what the arm means are by taking more samples from the arms, the error approaches 0. So that's what we were plotting on the y-axis. And the error starts out big and then approaches 0. And then we are also plotting these vertical lines, which essentially is how much time it takes for these errors to reach 5% of their final error. So if we think of these errors approaching like an asymptote, we can plot how long it takes to reach within the 5% of that asymptote. And then we see that. So we are looking at the performances of all of the heuristic methods and the optimization methods and FMMC and FDLA that do result in slightly better performance than the other heuristic methods. But it's in the 1 or 2 steps range. So you have to go through all of the process of optimization through the convex optimization method in order to gain this performance gain. So let's look at the rest of the networks and how FDLA and FMMC, what performance does using FDLA and FMMC results in. And we see that in all of these cases, it's similar to before. FDLA and FMMC result in very, very small or negligible increases or gains in terms of how fast they reach within the 5% of the final error. But there's also other cases where using FDLA and FMMC does not result in any performance improvement at all. So in this case, actually, they are worse than some of the other heuristics. So we think that this might be due to small network sizes. So we are only looking at networks that have 5 agents or 8 agents. So let's try with 50 agents. And so we use the Erdos-Renyi model. It's a randomly it's a model to generate random graphs. So we select a large 50 node network, and then we see that it still does not result in better performance. And so it is on the same level as some of the other heuristic methods, but also worse than, say, constant degree, constant edge, and local degree in this case. So why does this happen? So we try to examine the properties of these graph networks that we're looking at. So we look at the node centralities, and we see that there's high closeness centralities in all of the nodes in the small and the large network, large randomly generated 50 agent network. So that means the information from one end of the network can reach very, very fast to the other end of the network. So any noisy information or any estimates from one end of the network, it propagates very, very fast. So we consider networks with a communication constraint. So what we do is we take clusters, small clusters of networks, and then we join them using only a singular pair. So how that looks like is in this fashion. They look like star networks, but essentially each of the leaf nodes is another cluster. And so what happens, what we can see here is that the parent nodes have very high betweenness centrality. So they are doing a lot of heavy work to ensure that the information from one cluster gets to the other clusters. So the individual clusters can reach a consensus on their own. For the entire team to reach a consensus, the central parent nodes have to do a lot of the heavy lifting in terms of communicating that information across. So now we can take a look at the performance gains here. And in all of these cases, FMMC does better than the heuristic methods. So the number of exact time steps is greater than in the case of the smaller networks. And FDLA also results in better performance in 2, 3, and 5 clusters, but not in 4 clusters. So there's still a little bit of inconsistency in terms of whether FDLA does better or not, but FMMC consistently results in a decent amount of performance improvement over the heuristic methods. However, there's still one thing that these don't account for, which is noise in communication. So when we say noise, it can be noise in observations, so that because the agents are sampling from normal distributions, they're inherently not the exact true reward value that you're receiving. It is a distribution. But there can also be any malfunctioning agents or malicious agents that are trying to throw off the team as a whole. So, and neither co-op-PCB2 nor the edge weight setting methods try to consider or account for this noisy communication. However, we have another algorithm called LMSC, least mean square consensus. This algorithm is also similar to FDLA and FMMC in that they also try to formulate this problem into a convex optimization problem. So first they start by modeling noise, like what is noise? So we have the basic idea of decrude learning here. So the next state is relying on the current state multiplied by the P matrix, but you also add in this noise variable, VT, which is also sampled from a normal distribution. And when you have this additive noise from external sources or within the team, we can calculate the mean square deviation from the node states from what the average should actually be. So if you recognize this formula, this is the same as mean square deviation or mean square error in machine learning. And so this is how far away are the current node states deviating from the average of the initial node states. So, and then this is shown to reach some steady state value. And so we can try to minimize this steady state value. And so in that process, LMSC tries to first rewrite P into a parameterized form, and then comes up with this minimization algorithm. So this is also a convex optimization problem. So we're trying to minimize the steady state deviation given P, and the steady state deviation is given by this formula, which also relies on the eigenvalue of the P matrix. And this is also subject to the same constraints as before. So the matrix must be symmetric, the rows must add up to 1, and the spectral gap must be less than 1. And just like FDLA, this one also does not require edge weights to be non-negative, so they just can result in negative edge weights. So how do we simulate noise in multi-agent multi-armed bandits? So now that we have a way to deal with noise, we want to introduce a little bit of noise to try to see what kind of performance gain does this optimization result in. So we add noise by if you can read this, so this is the reward that is received at every time step. And the reward is sampled from a normal distribution given the true mean of the arm and the standard deviation, which is usually 1. And we add this noise variable VT, just like we saw in the formulation of the degree learning. And this VT is sampled from just a unit normal distribution. And here are some results for house, ring, and path. And here, using LMSE results in better performance across the board, and actually a significant performance improvement in ring and path in terms of how fast they reach 5% of the error. On the other hand, there's also all-to-all star and 8 agents, where using LMSE is about the same as some of the other heuristics, or worse than some of the other heuristics. And I just want to point out, keep in mind the performance of star, because we'll see that in the large cluster networks, LMSE still does not perform well, because these also inherit the similar properties of star. And using LMSE actually results in worse performance as the number of clusters grows. So in 2 clusters, LMS is actually somewhat comparable to some of the other optimization heuristic algorithms, but it starts falling off in 4 clusters and 5 clusters and so on. So when we actually examine how these edge weights look like, there's a high negative edge weight in the edges that are connecting from the clusters to the central node. So because these cluster networks inherit properties of both star and some other networks with high closeness centralities, you need kind of a hybrid method to set these edge weights, but LMSE does not support that. So what do we take away from this one? These experiments, the effect of optimization is very, very highly dependent on what the structure of the exact network is. And they result in either small performance improvements or inconsistent improvements. So this can be beneficial in applications where even small performance gains are very, very important to the application, but we like to do better. So revisiting some of the shortcomings, we mentioned some points in the initial motivation of this problem, which is that we want agents to be capable, we want to consider agents that have different capabilities based on the kind of problem that they're attacking. So the edge weight setting methods do not account for the competencies of the nodes. So take this, for example, take an RGB camera, which is very good at, for example, say scanning images in broad daylight, but it falls off in the night dim lighted zones. However, a thermal imaging camera will be really good in nighttime, but may not be good when the temperature is same when in the subjects in its field of view. So we want to kind of consider these competencies or capabilities in multi-armed bandits. So what does competency mean? We say, so in general terms, competency means the ability of an agent to achieve its goal with high probability and with finite resources. So we take a parallel approach in the multi-agent multi-armed bandit context, and we say that the competency of an agent in the multi-armed bandit context is how fast the agent determines what the best action to take is in a finite time. And we say that the competency value ranges between 0 and 1, 0 being low competency and 1 being high competency. And so an agent with competency 0 means it takes very long to find out what the best arm is, but an agent with high competency, so closer to 1, will take much shorter time. And in co-op UCP2, we propose that agent competency formulation, how it looks like, would be to use the competency value of the actual agent with some additive noise in order to obfuscate the true payoff information. So it becomes harder for the agent to figure out what the best arm is if they are kind of blended in together, when it cannot obtain what the true average payoff is, even in the long run. So this is a formulation. So the reward given the competency of an agent and the arm that they picked is sampled from this normal distribution. So there's the, if you can notice, so there's the true mean of the arms, and then that is multiplied by the competency of the agent itself, plus some additive noise. So these noise variables are important because we have done some preliminary testing where these noise variables are excluded, and it's only the true mean of the arms multiplied by the competency. And so essentially what it does, the effect that it has is that the competency kind of translates and scales the normal distributions of the arms. And this is not significant, as we'll see in the next slide. So we need these noise variables to kind of obfuscate or even jumble the true means of the distributions. So here we have three different plots. So the first setting is for the perfect agents, where the competencies of all the agents is 1. And then we have the naive formulation, where we have the same formulation as the previous, as this one, but without the noise variables. And then we have the final formulation, which is what we come up with, which is it takes into account the competency of the agents and the noise variables. And we see that, so on the left-hand side, we have the same plot as before. It's the error, how the error changes from the start till the end. And we see that between the perfect agents case and the naive formulation, when the agent and when agent 1 is the less competent agent, the error does not change that much in both of these formulations. So even if you have a less competent agent, which has a competency of 0.5, and the others have a competency of 1, it does not really affect the team that much. And when we take a look at the percentage of the time the optimal action was taken, so over the horizon of 1,000 time steps, we see that some of the agents actually end up doing better than the perfect case. And we think that this is probably due to the additive exploration, or the additive noise that encourages exploration in the long run. That results in slightly better performance. However, with our final formulation, when we introduce noise variables, we can see that a single less competent agent affects the entire team negatively. And we can see some patterns in the percentage of the time they select the optimal action, which is that agent 1 does the worst, as expected, because it itself is a less competent agent. Agent 2 does the next worst, because it's directly communicating with agent 1. And agents 3 and 4 are the best overall, because they're indirectly being affected by agent 1. But they also have each other to support, or they get good information from agents 3 and 2, for example, for agent 4. And so they're able to do slightly better than the rest of the team. So as we mentioned before, we want to consider agents with different competencies. So now we have a way to formulate competency, but we also want a way where the competency changes based on the kind of problem or the stage of the problem that they're playing. So what we say is that each agent has a vector of competencies. So it has a competency value per stage, so the per stage that they're going to be playing. But what is a stage? We need to be able to define what a multi-armed bandit stage means. And one way that we propose we can do that is by using the bandit difficulty rating measure. So we say that, so not all multi-armed bandits are created equally. Some are more difficult to figure out what the best arm is than the others. And this is essentially dependent on how far away the distribution of the best arm is from the rest of the arms. So if you, and we'll develop an intuition in the next slide, but essentially what we rely on here is the total variation distance of the probability measures. We take into account the total variation distance of normal distribution specifically, and we utilize this in our final formulation, which is the difficulty of a given multi-armed bandit. And essentially what this does is we take the average total variation distance from the best arm to the rest of the arms in a multi-armed bandit. And then since the total variation distance is greater when the arms are farther apart, and the bandit is actually easier when the arms are farther apart, we invert the scale. So as the distance grows, the value shrinks. So it is 1 minus this distance. So we'll see more clearly in this case where we have 2 multi-armed bandits. The first one is an easier bandit because it has arm means 1, 2, and 4. And 4 is further away from 1 and 2. And so there's less overlap in the actual probability density functions of these arms. However, in the second multi-armed bandit, you have arm means 1, 3, and 4. And 3 and 4 are overlapping a lot. So this means that the samples that we get from these arms have a higher chance of overlapping with each other. And the agent has a harder time to figure out what the best arm is. And we can also see the results in terms of percentage of the time they select the optimal action and in the error of the estimated mean of the best arm. So in terms of the percentage of optimal action, we consider just a single agent, a single UCB agent that is playing both of these arms, or bandits, excuse me. And it has an easier time getting a higher percentage of optimal action on the first bandit than on the second bandit. And similarly, in the error, we notice that it takes less time to reach 5% of the final error when playing the first bandit than when playing the second bandit. So now that we have developed an intuition on how this works, we can actually control how far away these arms are placed from each other. So if we sample the arm means of any given bandit from another normal distribution, and we can control the scale of this distribution in order to define how closely these arms should be. So if we sample the multi-armed bandit arms from a more narrow distribution, for example, the blue distribution here, which has a mean of 0 and scale of 0.5, we essentially force the distributions of the underlying arms to overlap a lot compared to when we say sample the bandit arms from a more wider distribution. And so when we plot the distribution difficulties over here, a histogram of these difficulties, we see that the bandit sample from a more narrow distribution results in bandits that are more difficult than the others. And so, so now that we have both a way to represent the competencies of agents and also a way to say what a multi-armed bandit stage is, we want to see how we can optimize the edge weights in this scenario when taking into consideration both of them, and also test the performance in the long run. So, as we discussed before, each agent has a vector of competencies based on the stage, and we need a long-term optimization. So we come up with this method, which is for each bandit stage. So that means, say, if we sample bandits from 3 different normal distributions, we say that a team can go out and play a batch of these bandits from each of these stages, and then kind of look at the emerging team performance, and then use that to optimize and tweak the edge weights of the team internally. And that happens in an iterative loop per bandit stage because competencies change per stage. And when the optimization results in team performance that levels off over time, we say that then the team is optimized. So now that we have this method, we want to go reevaluate some of the constraints. The first one is we want to make the edges directional, and we'll see why this is important in a bit. And the rows must add up to 1, just like before. And we disallow removal or zeroing of edges. So this is to not isolate any of the lesser competent agents. And this is because if we do not impose this constraint, there's a higher chance of just trying to isolate the lesser competent agent from the team and improve the team performance just with the good agents. So let's take a look at how the optimization affects, or what edge weights the optimization results in. So we take the initial case where we have a simple triangle network, 3-agent network, and the initial edge weights are set using FMMC, fastest mixing Markov chain. And in this case, all the edge weights are set to be 0.33. And we consider 3 different bandit stages, and we see that it's the same stage as before. Stage 1 is the most difficult, so it's the blue color distribution with a smaller scale. Stage 2 is the orange distribution, and stage 3 is the widest distribution in gray color. And in each of these stages, so in stage 1, agent 1 is the less competent agent. In stage 2, agent 2 is the less competent agent. And in stage 3, agent 3 is the less competent agent. And all the rest of the team is more competent, so it has competency 1.0. And the less competent agent is actually 0.5. So in the first stage, when the agent 1 is less competent, we see some interesting behavior. So what we see is that the edge weights, or the weights of the edges that transfer information from neighboring agents into this less competent agent is minimized. So, or excuse me, it's the opposite. So the edge weights, or the weights of the edges for the information going away from agent 1 to agents 2 and 3 is minimized. And this is so that because agent 1 is less competent and it's propagating noisy information. So the rest of the team wants to minimize or take or kind of restrict this information into affecting its own estimates. And on the other side, we also see that the edge weights, or the weights of the edges going from agents 2 and 3 into 1 is maximized. And this is so that these two agents who have more accurate estimations, they can propagate more useful information back to agent 1 and kind of increase their team performance as a whole. And this is also reflected in these two stages, where agent 2, the noisy information coming out from agent 2 is restricted, and the helpful information coming out from agents 1 and 3 is propagated more into the other agent. And so we'll take a look at the similar plots for stage 1 in this case. We run experiments where we optimize the edge weights using the heuristics and the optimization methods, which is FMS, CFTLA, and LMSC, or not LMSC in this case because it doesn't take into account agent competencies. But we have our own optimization algorithm, which is represented by OPT. And we see that using the optimization method, which takes into consideration what the agent competencies are, results in much better performance because it is restricting the information or the noisy information coming from less competent agents and providing it more helpful information. And similarly, when we take a look at the errors or how the error and the estimate of the best term mean changes over time, it is much less compared to the other algorithms. And this also carries across stages 2, where using the optimized edge weights results in better performance, and stage 3. So what are the takeaways? So there's a significant team performance improvement over previous edge weight setting methods because we take into account these competencies and that are changing over multiple stages. And we also see some of the emergent behaviors, which is that the information coming from less competent agents is restricted, and the information going to the less competent agent is maximized. So before I wrap up, I want to talk about a little bit of the future work. So one potential area that this could be extended to is using asynchronous communication. So in this case, co-op-TCP2 only works by agents communicating all at once in a given time step, but in real world, it may not be the case. And since we're striving towards making this more closer model to the real world scenarios, we want to be able to have able to take into account also asynchronous communication. We also want to consider dynamic environments. So in multi-armed bandits, actually, this can be thought of as a non-stationary bandit where the means of the bandit change over time. So you may not always be looking at the same true means for all of the bandits. So you may have to reevaluate your estimation strategy and try to optimize the team performance. You can also look at multi-agent optimization, multi-objective optimization, which essentially is you're optimizing team performance, but the individual agents may also have their own objective or cost functions that they have to optimize towards. So taking into account multiple of these objectives may also be an interesting problem. And it will also be interesting to see real world applications. And so how does this apply to real world multi-human or multi-agent team formations? Some technological details. So all of the experiments in this work have been implemented in Python using a NumPy computation, CVXPy for convex optimization, Matplotlib for all of the plotting, and NetworkX for the graph networks. We also accelerated all of the experiments using a library called Number, which is a just-in-time compiler for Python and NumPy. So what this does is essentially speed up the runtime of the code by several orders of magnitude. And you can also easily implement parallel processing. And since we are taking an average over several thousand runs, this is a significant improvement in terms of how fast the code runs. So several days to a few seconds. And we also have a paper acceptance. So the first part of this thesis, so that includes optimizing using FMM-CFTLA in team structures and taking a look at the large cluster networks, has been accepted just a few days ago in the MECC conference. And thank you for listening.
All right, thank you for the great presentation. All right, we'll open up to questions from public. You have people on Zoom?
There are 5 people on Zoom.
Okay, they also, do they hear us?
Yes, they can hear us. Yeah.
Okay.
So if anyone has any questions, feel free to speak up or put their questions in the chat. But we'll start with that.
Yeah. So in the agent evaluating agent competencies, right? You mentioned that you didn't want to zero out agents. I guess thinking about the real world, like maybe there's a robot or something that has a faulty sensor and it just has bad information.
Right.
So I saw that the weights got like really low. We got like 0.01.
Yeah.
But why not have them go to 0?
So that is a good point. We don't want to go to 0 because we also because if this can be extended to where we have, say, the agents that have like a competency profile when the competency goes back up again, which we want to be able to detect that and then maybe try to pipe that good information back in. But also that part came up before we try to make the edges bidirectional or directional, I mean. So when we only have singular undirected graphs, then if you zero out that edge, the agent is isolated. But if you have both edges going in and out, so if you look at just directional edge weights, then it might be more preferable to have that edge completely zeroed out, but we haven't really delved into that yet.
So did any of your experiments have the competency change in a single bandit or no?
No, in this case, we only take a look at competency that stays the same throughout like a single stage.
Would it still work if it changed like halfway through, you think?
I think it would change if it is actively optimizing over that network, because it is taking a look at the output of the or the output team performance. But if it has optimized and if you're not modifying the edge weights anymore and then play the actual bandit from the problem stage, then it would not work anymore because we're not tweaking the edge weights.
And on this note, Monish has been telling me about his thesis for basically a year. So this is one type of question I like to ask. Do you have like a favorite theoretical usage of this where this would actually be good?
That's a really good question. I've been trying to, so on a project that I am working on, it's called AI caring. Basically, what it means is, what it focuses on is using AI and robotics to help the lives of older adults, especially with mild cognitive impairments. So I think this could be useful in that case where you have like a competency of a human or an agent. I don't know how insulting that is to the older adults, but when you're trying to work with an older adult or like a network of humans and other potential robots too, it might be useful to be able to take into account how much they are capable of performing the task that they want to perform, and how much can we help in order to help them reach their goal. So it was. We do have a project that is starting right about now, but it is not at the stage where we can apply like the abstract concepts that we look at in this case.
Makes sense.
Yeah.
Other questions?
Zoom.
Why I'm the general public right now. So you talked about communication constraints in the first part of your talk, right?
Yes.
What does a communication constraint mean?
So in this case, a communication constraint is essentially the properties of these p-matrices. We restrict them so that the consensus, the reaching of consensus when using these communication matrices, it is guaranteed. So the convergence to consensus is guaranteed only under these specific constraints. And the mathematical proof is a little bit more detailed, but essentially throws have to sum up to 0. So in some cases, the edges have to be, the edges cannot be non-negative, and they have to be symmetric. And these communication constraints, if we're talking about real world, like what does this mean in an actual case where robots are communicating with each other? It's still similar. So we don't want when they're trying to mutually or cooperatively estimate these true means, we don't want the convergence to consensus to never happen. And it's only guaranteed under these specific communication constraints.
The one thing you mentioned was you went from small networks to large networks with a single node that has high centrality. Right. So one thing that popped into my head was, why is centrality an issue in terms of communication constraints? Shouldn't it be the shortest path length that basically tells you what the communication constraint might be? But it takes longer to communicate the information rather than there being a central node through which information needs to be shared. So that's the first part, is the shortest path length. That's what you should be considering. And if you're talking about communication constraint, you would think about bandwidth, like the central node has a certain capacity to transmit information, in which case it actually becomes a constraint.
I see. So in this case, constraints are more mathematical than like a practical constraint like bandwidth. But I suppose, so I have seen some works where the constraint actually means that all of the agents cannot communicate at once because there is a high network load. But in this case, it's still very abstract on like the bandwidth and the capabilities of communication in the network. And for the first part, which was the diameter or the longest or the shortest path, we did experiment with trees, which do have the maximum diameter, I suppose, but the optimization effect was not quite apparent in trees. But it would be interesting to explore more into what kind of other networks. We have stopped at the looking at only the large cluster networks. But yes, I do agree that using or having a larger diameter might be interesting because it takes so long to get from or reach consensus for one part of the network to the other.
So in real time, how much longer did like the 50 network one take to optimize than like the 5 with the 8s?
So optimization, it takes a few minutes for the large networks. These experiments are really not that computationally heavy. Yeah, so it's just that with larger networks, you have bigger matrices multiplying with each other, and that is like once you go past a certain size, you want it to be on the GPU, not on the CPU. So the overhead is actually matrix multiplication on CPU. So for the small networks, for comparison, it's actually like 30 seconds. For large networks, a couple of minutes. Yeah.
All right. So thank you, everyone. Please grab donuts and coffee on the way out.
And I can end the Zoom meeting now.
They should stop recording.
Stop recording.
But actually, your phone lived the whole time.
Nice.
15 minutes.
Nice.